Hello there. Today we'll begin our study of RSA, the first public key crypto system that was widely used in practice.
Chapter 7 on RSA is comprised of 5 video lectures. In V7a, we'll introduce the basic RSA encryption scheme and RSA signature scheme. In V7b, we'll summarize the state-of-the-art in algorithms for the integer factorization problem, whose hardness is necessary for the security of all RSA cryptosystems. V7c is about RSA encryption. We'll define what it means for a public key encryption scheme to be secure, and we'll present RSA OEP, a variant of the basic RSA encryption scheme that satisfies our security definition. We'll also present the RSA key encapsulation mechanism, RSA Chem. We'll study the RSA signature scheme in more detail in V7d. And lastly, video V7e will be a case study on a standardized RSA signature scheme, PKCS number 1, version 1.5, RSA signatures.
RSA was invented by Ron Rivest, Adi Shamir, and Len Adelman in 1977. This was the first practical public key encryption and signature scheme. Rivest, Shamir, and Adelman received the Turing Award for the invention of RSA in 2002. The Turing Award is the most prestigious prize in computer science. Another notable contribution of Rivest, Shamir, and Adelman was the introduction of the two main characters in cryptography, Alice and Bob. Alice and Bob make an appearance in most cryptography research papers, including those written in foreign languages. Here is an example of some text in Mandarin, Japanese, and Polish. Public key encryption schemes, such as RSA, have 3 stages: key generation, public key encryption, and decryption. Here is RSA key generation. Each entity Alice does the following. Alice randomly selects 2 large, distinct primes, P and Q, of the same bit length. I'll note that this can be done efficiently, but I won't cover prime generation in this course. Alice then computes the product n of P and Q, and the number phi, which is defined to be P minus 1 times Q minus 1. Phi is the Euler phi function of n. Alice then selects an arbitrary integer e between 1 and phi, and coprime with phi. She can do this by selecting arbitrary numbers e and verifying that e and phi are coprime using the Euclidean algorithm. She then computes the integer d between 1 and phi, such that e times d is congruent to 1 modulo phi. In other words, d is the inverse of e modulo phi. Such a d exists because e and phi are relatively prime. Moreover, d can be efficiently computed using the extended Euclidean algorithm. Alice's public key is the pair of integers n and e, whereas her private key is the integer d. We'll call n the RSA modulus, e the encryption exponent, and d the decryption exponent. Here is the RSA encryption procedure for the basic RSA encryption scheme. To encrypt a message for Alice, Bob does the following. He first somehow obtains an authentic copy of Alice's public key NE. Bob then represents the message as an integer m in the interval between 0 and n-1.
The requirement that the plaintext m be an integer between 0 and n-1 is not a major restriction on RSA encryption, because in practice, RSA public key encryption is typically used to encrypt symmetric keys. So, if m were an AES symmetric key, m would be 128, 192, or 256 bits in length, whereas in practice, the RSA modulus n is usually at least 2048 bits in length. So such m are less than n.
Bob then computes the ciphertext C as m to the power e modulo n. Bob can do this efficiently by the repeated square and multiply algorithm. Note that C is an integer in the interval between 0 and n minus 1. Finally, Bob sends C to Alice. To decrypt C, Alice does the following. She computes C to the power d modulo n, and the resulting number is in fact m. Note that encryption uses Alice's public key ENN, whereas decryption uses Alice's private key D. Therefore, anyone can encrypt the message for Alice, whereas only Alice can decrypt the ciphertext to get the plaintext. Here is a toy example of RSA key generation. Alice selects primes 23 and 37, computes her product n, which is 851, and phi, which is 792. She selects the encryption exponent e to be 631 and verifies that 631 and phi are coprime. She then computes d by solving this congruence modulo 792 using the extended Euclidean algorithm, and she obtains d equals 487. Alice's public key is a pair of integers n and e, and her private key is d. To encrypt the plaintext m equals 13 for Alice, Bob does the following. He first obtains an authentic copy of Alice's public key. He then computes the ciphertext C by raising 13 to the power 631 modulo 851. To do this, he first writes E in binary as a sum of distinct powers of 2. Then he computes successive squarings of 13 from 13 squared up to 13 to the power 2 to the 9. He then multiplies the appropriate squares of 13 together modulo n to get the ciphertext 616. Bob sends C to Alice. To decrypt C, Alice uses her private key to compute C to the power d modulo n using the repeated square and multiply algorithm. You can check that Alice obtains the plaintext 13.
To give you a sense of the size of numbers used in practice, here is an example of basic RSA encryption using a 2048-bit modulus n. Random 1024 is a maple routine that generates a random 1024-bit number. We'll first generate an RSA public-private key pair. R is a randomly selected 1024-bit integer, and P is the first prime after it. We'll then randomly select another 1024-bit integer and set Q to be the first prime after it. N is the 2048-bit product of P and Q. Phi is P minus 1 times Q minus 1. We'll select the encryption exponent E to be 2 to the power 16 plus 1. This encryption exponent is commonly used in practice. We'll check that E and phi are coprime. And then, we'll use the extended Euclidean algorithm to find integers d and y that satisfy E times d plus phi times y equals 1. We'll reduce d modulo phi to ensure that it is a non-negative integer less than phi. And check that E times d is congruent to 1 modulo phi. So, Alice's public key is the pair of integers n and e, and her private key is the integer d. Let's encrypt this plaintext M of all sevens. So, we'll compute the ciphertext C by raising M to the power E modulo n. Maple uses the repeated square and multiply algorithm to do this. To decrypt C, we'll compute C to the power D modulo n. As expected, decryption recovers the plaintext M.
Here is a proof that RSA works. We'll prove that for all integers m between 0 and n-1, if C is defined to be m to the power e modulo n, then C to the power d modulo n equals m. So when plaintext M is encrypted to ciphertext C, and then C is decrypted, you get back the plaintext M. The proof relies on Fermat's little theorem. Recall from V6b that if p is a prime number, and m is an integer that is not divisible by p, then m to the power p minus 1 is congruent to 1 modulo p. We'll prove that m to the power ed is congruent to m modulo n for all integers m between 0 and n-1. We'll first note that since e times d is congruent to 1 modulo phi, we can write e times d as 1 plus k times phi for some integer k. Since e and d are both greater than 1, their product is also greater than 1. Thus, since p and q are at least 2, we have p times 1 times q minus 1 is at least 1. It follows from this that k must be at least 1. Okay, so we'll first prove that m to the power ed is congruent to m modulo p. Suppose first that p divides m. Then, m is congruent to 0 modulo p. And raising both sides to the power ed gives us that m to the power ed is congruent to 0 modulo p. Thus, we can conclude that m to the power ed is congruent to m modulo p. Suppose next that p does not divide m. Then, since p is prime, we can invoke Fermat's little theorem to conclude that m to the power p minus 1 is congruent to 1 modulo p. Raising both sides of this congruence to the power k times p minus 1, and then multiplying both sides by m, gives us that m to the power k times p minus 1 times q minus 1 plus 1 is congruent to m modulo p. Replacing the exponent by ed gives m to the power ed is congruent to m modulo p. So we conclude that m to the power ed is congruent to m modulo p for all integers m. Similarly, m to the power ed is congruent to m modulo q. Now, this congruence tells us that p divides med minus m, whereas this congruence tells us that q divides m to the ed minus m. And so, since p and q are distinct primes, we can conclude that p times q divides m to the power ed minus m. Thus, m to the power ed is congruent to m modulo p times q. And this proves that RSA decryption works. So we've proven that RSA decryption is the inverse operation of RSA encryption. Raising c to the power d modulo n inverts the operation m to the power e modulo n. RSA encryption can be described as computing the eth power of the plaintext m modulo n, whereas RSA decryption is computing the unique eth root of the ciphertext c modulo n. I'll next describe the basic RSA signature scheme. Key generation is the same as for RSA encryption. So Alice has a public key NE, and her private key is D. To sign the message M, which can be of arbitrary bit length, Alice does the following. She first computes the hash M of the message m. Here, H is a cryptographic hash function such as SHA-256. Alice then computes the signature S on M by raising the hash value to the power D modulo n. She can do this efficiently by the repeated square and multiply algorithm. Note that in practice, the hash value M is smaller than the RSA modulus n. For example, M might be 256 bits in length, whereas n might have bit length 2048. Alice's signed message is M and S. Here, M is the message and S is its signature. Observe that signatures are message dependent, because the signature depends on capital M, which depends on the message M. To verify Alice's signed message, any user Bob can do the following. Bob first somehow obtains an authentic copy of Alice's public key NE. He then hashes the message M to get the hash value capital M. He raises S to the power E modulo n to get M primed. Finally, Bob accepts the signed message if and only if M equals M primed.
Observe that Alice's signature S is the unique ETH root of the hash value of the message modulo n. Alice can compute these ETH roots since Alice knows D. Thus, S to the power E modulo n should be capital M. And then if Alice indeed signed M to get S, then M prime should equal M, and Bob will accept the signed message. In V7b, we'll present an overview of the state-of-the-art in integer factorization algorithms, and will give a brief history of factoring. The running time of the fastest factoring algorithm lets us determine the bit lengths of RSA moduli for a given level of security. I'll see you later.